Course objectives.
Let's take a look at some of the basic goals of this course. 1. You'll dive into the basics of logic design, focusing on essential gates like AND, OR, NOT, NAND, NOR, XOR, and XNOR, and how they contribute to creating digital circuits. The course will guide you through designing and analyzing combinational circuits using Boolean algebra and Karnaugh maps. Advanced topics include circuit design with NAND and NOR gates, understanding hazards in combinational circuits, and exploring flip-flops used in sequential circuit design. You'll also learn about mealy and more sequential circuits, state equivalence, optimization techniques, key timing considerations, and the role of tri-state buffers. You'll be able to apply these principles effectively to design and optimize digital circuits. 2. Understand the basics of hardware description languages, HDLs, and how Verilog is used to design digital systems. You'll learn to describe hardware designs using Verilog's core language constructs, including module definition, design hierarchy, and behavior description. The course will also teach you how to synchronize and communicate between different parts of a design using Verilog. Additionally, you'll learn the rules for using identifiers, comments, and whitespace in Verilog code, ensuring you can effectively describe and configure simple designs. 3. You will learn how to design combinational logic circuits using Verilog. You'll understand how to implement basic logic gates using assigned statements and explore more advanced components like multiplexers, demultiplexers, encoders, and decoders. You will also learn how to use shift operations, majority logic, and comparators to build efficient combinational circuits. By studying these techniques, you will gain the practical skills needed to design and implement a variety of combinational logic circuits in digital systems. 4. You will learn how to design and analyze sequential logic circuits, which are essential for storing and processing data. You will explore key components such as latches, flip-flops, registers, and counters, understanding how they operate and are used in digital systems. Through practical examples, you will also gain insight into metastability in bistable circuits and how pattern sequence detectors function in sequential logic. These skills will help you design reliable and efficient sequential circuits for a wide range of applications. 5. You will learn how to design arithmetic circuits using Verilog, focusing on essential operations like addition, subtraction, multiplication, and division. You will explore binary number representation and understand how both signed and unsigned numbers are handled in arithmetic operations. Additionally, you will gain insight into fixed point and floating point numbers, as well as binary coded decimal, BCD, representation. You will have a solid understanding of how to design and model efficient arithmetic circuits. 6. You will learn how to design and implement finite state machines, FSMs, which are circuits that move between predefined states based on input values and clock signals. You will explore how FSMs control transitions between states and how these transitions are determined by a sequence of inputs and logic conditions. You will also understand how FSMs store past states to make decisions about future actions, making them more efficient than simple logic circuits. You will be guided in coding different FSM components, such as state memory, next state logic, and output logic, to solve real-world design problems like sequence detectors and controllers. 7. You will have a strong understanding of how to design and implement synchronous sequential circuits, such as Moore and Mealy machines. You will learn how to identify equivalent states, simplify state machines, and apply synthesis procedures to optimize logic design. Additionally, you will explore the design and operation of synchronous registers and counters, gaining practical experience through various examples. This knowledge will enhance your ability to create efficient, reliable digital systems using Verilog. 8. You will have a comprehensive understanding of asynchronous sequential machines and how to design them without the need for a synchronizing clock. You will learn about the synthesis process, including handling hazards, oscillations, and race conditions that may arise in circuits. You will explore real-world examples and analyze techniques for reliable data transfers between devices operating at different speeds. 9. You will understand how to design digital systems by combining smaller circuits like registers, counters, and multiplexers into larger functional units. You will explore the role of the data path in storing and transferring data and learn how control circuits manage the operations of the data path. By studying examples like simple processors, multipliers, and dividers, you will develop the skills needed to design efficient and reliable digital systems for various applications.